Welcome to Module 2, where we'll delve into deep learning, the cutting edge of artificial intelligence that has powered many of the recent breakthroughs you've heard about, from image recognition to advanced language models. So, what exactly is deep learning? It's a specialized branch of machine learning that uses artificial neural networks with multiple layers, hence deep. Unlike traditional ML algorithms that often require manual feature engineering, deep learning models to automatically learn intricate patterns and representations directly from raw data, whether it's images, text, or audio. Think of it as mimicking the human brain's structure. Our brains have billions of interconnected neurons, organized in layers, processing information hierarchically. Deep learning networks are designed with a similar layered structure, where each layer learns to detect different features or aspects of the input data, building up from simple patterns to complex ones. For example, in an image recognition task, an early layer might learn to detect edges. A subsequent layer might combine edges to detect shapes, then another layer might combine shapes to detect parts of an object until finally the network can recognize a full object like a face or a car. This hierarchical feature learning is a key differentiator. Deep learning has revolutionized fields like computer vision and natural language processing, achieving performance levels previously thought impossible. In the next lecture, we'll start building these fascinating networks from the ground up. To understand deep learning, let's start with the fundamental building block, the artificial neural network, often called a feed-forward neural network or a multi-layer perceptron. We'll explore its architecture and how information flows through it. At its core, an ANN is composed of interconnected neurons, also called nodes. These neurons are organized into layers. We typically have an input layer, where our raw data enters the network. This layer doesn't perform computations. It simply passes the input values forward. Following the input layer are one or more hidden layers. These are where the magic happens. Complex computations and feature transformations occur. Each neuron in a hidden layer receives input from the previous layer, performs a calculation, and then passes its output to the next layer. Finally, we have the output layer. This layer produces the network's prediction or classification. The number of neurons in the output layer depends on the problem. One for binary classification or regression, multiple for multi-class classification. Now let's look inside a single neuron. Each input connection to a neuron has an associated weight. Think of weights as the strength or importance of that input. The neuron multiplies each input by its corresponding weight and sums these products. This sum is then added to a bias term, which allows the neuron to activate even if all inputs are zero, or shift its activation threshold. This weighted sum plus bias is then passed through an activation function. The activation function introduces nonlinearity into the network. Without it, stacking layers would just be like stacking linear equations, resulting in only a linear model. Common activation functions include ReLU, rectified linear unit, which outputs the input directly if positive, otherwise zero, and sigmoid, or softmax for outputs, squashing values between 0 and 1. The process of information moving from the input layer through the hidden layers to the output layer is called forward propagation. It's how the network makes a prediction for a given input. In summary, an ANN is a series of interconnected neurons, each performing a weighted sum of its inputs, adding a bias, and passing it through an activation function. This creates a powerful system capable of learning complex, nonlinear relationships. But how do these weights and biases get adjusted to learn? That's what we'll cover in our next lecture, backpropagation. We've seen how a neural network makes a prediction through forward propagation, but the real power lies in how it learns, how to adjust its weights and biases to improve its predictions. This process is driven by backpropagation and optimization algorithms. After the network makes a prediction during forward propagation, we compare it to the actual correct output, the ground truth. The difference between the prediction and the actual value is called the error or loss. A loss function quantifies this error, for example, mean squared error for regression or cross entropy for classification. The goal of learning is to minimize this loss. This is where backpropagation comes in. It's an algorithm that efficiently calculates the gradient of the loss function with respect to every weight and bias in the network. Think of the gradient as the slope or direction that tells us how much to change each weight to reduce the loss. Backpropagation works by propagating the error backwards from the output layer through the hidden layers all the way to the input layer. At each neuron, it determines how much that neuron's weights contributed to the overall error. It leverages the chain rule from calculus to compute these gradients efficiently across all layers. Once we have these gradients, an optimization algorithm uses them to update the weights and biases. The most fundamental is gradient descent. Imagine you're blindfolded on a mountain trying to find the lowest point. You take small steps downhill, constantly checking the slope. Gradient descent does precisely that. It takes small steps in the direction opposite to the gradient downhill, effectively reducing the loss. The size of these steps is determined by the learning rate, which is a crucial hyperparameter. A large learning rate can overshoot the minimum, while a small one can make learning very slow. There are many variations of gradient descent, such as stochastic gradient descent, SGD, which uses small batches of data, and more advanced optimizers like ADAM, which adapt the learning rate for each weight individually, leading to faster and more stable training. This iterative process of forward propagation, making a prediction, calculating loss, backpropagation, calculating gradients, and weight updates using an optimizer is repeated thousands, sometimes millions of times across epochs, until the network's performance converges and the loss is minimized. This is how neural networks learn from data, making them incredibly powerful tools. Up next, we'll see how deep learning connects with other areas of AI. While standard ANNs are powerful, they have limitations, especially with high-dimensional data like images. This is where convolutional neural networks shine. CNNs are a specialized type of neural network, specifically designed to process data with a grid-like topology, such as image pixels. The core innovation of CNNs is the convolutional layer. Instead of connecting every input pixel to every neuron in the next layer, a convolutional layer uses small filters, also called kernels, that slide across the input image. Each filter detects a specific feature, like an edge, a corner, or a texture, anywhere in the image. Imagine a 3x3 filter moving over a larger image. At each position, it performs a dot product between the filter's values and the corresponding pixels in the image. The result is a single number in an activation map or feature map. This process is repeated with many different filters, creating multiple feature maps, each highlighting a different pattern in the image. A key advantage of convolution is parameter sharing. The same filter is applied across the entire image. This significantly reduces the number of parameters compared to a fully connected network, making CNNs more efficient and less prone to overfitting, especially with large images. It also makes them robust to shifts in object position. After convolutional layers, CNNs often include pooling layers, most commonly max pooling. A pooling layer downsamples the feature maps, reducing their spatial dimensions. For example, in max pooling, it takes the maximum value from a small window, e.g. 2x2, within the feature map. This helps to make the network more robust to small variations in position and reduces computational load. A typical CNN architecture consists of alternating convolutional and pooling layers, gradually extracting higher-level features and reducing spatial dimensions. Finally, the extracted features are often flattened and fed into one or more fully connected layers, similar to a standard ANN, for classification or regression. CNNs have achieved remarkable success in computer vision tasks: image classification, identifying what's in an image, object detection, locating objects, and facial recognition. They form the backbone of technologies like self-driving cars, medical image analysis, and visual search. Understanding CNNs is crucial for anyone working with image or spatial data. Their ability to automatically learn hierarchical features has truly transformed the field. Next, we'll explore recurrent neural networks, which are designed for a different type of data, sequences. While CNNs master spatial data, like images, what about sequential data, like text, speech, or time series? This is where recurrent neural networks, or RNNs, come into play. RNNs are designed to handle sequences by maintaining an internal memory of previous inputs. The key idea behind an RNN is recurrence. Unlike feed-forward networks where information flows in one direction, RNNs have loops, allowing information to persist from one step of the sequence to the next. Imagine processing a sentence word by word. Understanding a word often depends on the words that came before it. An RNN's hidden state acts as this memory. At each time step, an RNN takes the current input, for example, a word, and the hidden state from the previous time step. It combines these to produce an output for the current step and an updated hidden state that's passed to the next step. This makes RNNs suitable for tasks like predicting the next word in a sentence, machine translation, or analyzing time series data. However, traditional RNNs suffer from the vanishing gradient problem. As information propagates through many time steps, gradients can become extremely small, making it difficult for the network to learn long-term dependencies. This means they struggle to connect information from many steps ago to the current prediction. This led to the development of long short-term memory networks, or LSTMs. LSTMs are a special type of RNN designed to overcome the vanishing gradient problem and effectively learn long-term dependencies. They achieve this through a sophisticated internal structure called a cell state, which acts as a conveyor belt for information. LSTMs have multiple gates: input gate, forget gate, and output gate, that regulate the flow of information into and out of the cell state. These gates learn which information to remember and which to forget, allowing LSTMs to retain relevant information over long sequences. This capability made LSTMs incredibly popular for a wide range of NLP tasks before the advent of transformers. While transformers have now largely surpassed RNNs and LSTMs for many state-of-the-art NLP tasks, understanding RNNs and LSTMs provides crucial context for how models evolved to handle sequential data, and they remain valuable for certain applications, especially time series analysis. Now let's explore some deep learning case studies. Deep learning has propelled AI into realms previously only imagined. Let's look at 5 impactful case studies showcasing its transformative power across various industries. Case Study 1. Image recognition in healthcare. Deep learning, especially CNNs, is revolutionizing medical diagnosis. Models are trained on vast datasets of X-rays, MRIs, and CT scans to detect diseases like cancer, pneumonia, or diabetic retinopathy with accuracy comparable to or even exceeding human experts, aiding early diagnosis and treatment. Case Study 2. Natural language translation. Services like Google Translate leverage deep learning, particularly sequence-to-sequence models and later transformers, to translate text and speech between languages in real time. This has significantly broken down communication barriers globally. Case Study 3. Voice assistants, Siri, Alexa. When you speak to your voice assistant, deep learning is at work. It uses deep neural networks for speech recognition, converting audio to text, and natural language understanding, interpreting intent, allowing for natural conversational interfaces. Case Study 4. Recommendation Engines at Scale. While basic recommendation systems use foundational ML, giants like Netflix and Amazon use deep learning to process massive amounts of user data, movie genres, viewing habits, and product attributes to provide highly personalized and effective recommendations, driving engagement and sales. Case Study 5. Autonomous Vehicles. Deep learning is the brain behind self-driving cars. CNNs process camera feeds for object detection, cars, pedestrians, traffic lights, while other deep learning models fuse data from LiDAR and radar to perceive the environment, make navigational decisions, and control the vehicle in real time. These case studies highlight deep learning's ability to tackle highly complex problems, especially those involving unstructured data like images, audio, and text, and achieve superhuman performance in many domains. Next, we'll dive deeper into computer vision with AI.